Chapter 2, we only have 3 sections in Chapter 2. They talk about determinants and the use of determinants. We start with the definition. If A is a square matrix, again recall that square matrix means the number of rows equal the number of columns. Then the minor entry of A sub ij is denoted by minor f sub ij and is defined to be the determinant of the submatrix that remains after the ith row and the jth column are deleted from A. And the number -1 to the I plus j, where that's I and that's j, is denoted by C sub j and it's called the cofactor. Let me show you really quick how this plays. If you would like to find the determinant is denoted by sort of an absolute value. That's how we denote determinant. So if this is matrix A, we say the determinant of A, let's say you have A, B, C, D. So it's basically the product of this minus the product of this. Or they say this way, it doesn't really matter. And that's a number, a constant. You could also denote it by determinant of A. But if you put an absolute value instead of the symbol for the matrix, then that's reserved for determinant. Now, associated with every determinant is a list of signs. We call those the cofactors. To find the determinant of a 2 by 2, we know how to do that. It's right there. If it's more than 2 by 2, now there's a formula for 3 by 3, but if you don't want to use the formula, you pick a row or column. If you decided to pick this row, for example, then you multiply positive 1 times plus, that will be positive 1, and according to this theorem, you cross its row and column. You cross that row and that column, and you reduce it from 3 by 3 to a 2 by 2. And then, since I chose that row, negative times a positive is a -1, and you cross that row and column, and you're left with 3, 6, 0, 4. And you would go for the last, which is a positive. Positive times a positive is a positive 2, and you cross its row and column, and you're left with 3, 3, 0, 1. And this is positive 1 times, and this is 12 minus 6 minus 1. This is 12 minus 0. And this is a 2 and a 3 minus 0. So the determinant for this would be, let's see, 6 minus 12 plus 6. The determinant is a 0. Now we picked the first row. Somebody might look at this and say, well, wait a minute, I don't want the first row. I want the middle column. Well, whatever works. If I decided to take, and I'm not applying the theorem yet, I'm going to apply the theorem right now for you, but if I decided to go with, again, every time you want to do this, you need the cofactors. So you start with a positive and you alternate. There should be vertical and horizontal. There should be no two positives together or no two negatives. They're always alternating. If you decided to pick, what did I say? I forgot. Row 2, column. Let's say you decided to pick column 2. If you pick column 2, you have to take the cofactors. You pick -1 times 1, that's -1. You cross its row and column, 3, 6, 0, 4. Then you go to the next, that's positive times a positive is a positive 3. So you're multiplying those and you cross its row and column, 1, 2, 0, 4. And you would take, let's say, the last negative times a positive, -1, cross its row and column. That is 1, 2, 3, and 6. So that would be negative times 12 minus 0 plus 3 times 4 minus 0 minus 1 times 6 minus 6, and that would be negative 12 plus 12 plus 0, which is 0. There is no way of you doing this right and getting a different answer. No matter which row or column you pick, you will get a 0 in this case. There's no way around it. Now, I just want to make sure you see how the theorem applies. The theorem takes the cofactors, which are and call this m sub 1, 1. If you decided, so if I want to follow the directions, it says find all the minors and cofactors of matrix A. So this is the minor of 1, and a minor of 2. Here, minor of 1, 3, and 1. Again, any row or column that you pick will yield the same determinant. There's no way of you doing this using a different row or column and coming up with a different answer. Now, for a 2 by 2, we really don't do it. You could write it if you want, but we don't. Plus, minus, minus, plus. For a 3 by 3, 4 by 4, 5 by 5, we list those. Now, they want us to practice. Again, we're not going to do all of those. It says find all the minors and cofactors of the matrix. Let me show you really quick. If you decided to take m sub 1, 1, that'll be this m sub 1, 1. Well, that's going to be simply, if I cross its row and column, I'm looking at 3, 6, 1, 4. And if I look for, that's the minor. The cofactor would be, according to the formula, negative 1 raised to the 1 plus 1, which is negative 1 squared, and that's positive. So that's taking the place of those. So here I'll get, if I'm going to do this, I'll get 12 minus 6, which is 6, and it's positive. If I decided to take m sub, let's say 3, 1, that'll be this. Well, that one is going to be 0. There's no point in me trying to work it out, right? M sub 3, 1 would be simply cross 0 row and column. You're left with 1, 2, 3, 6. But then you're going to take 6 minus 6, that's a 0, right? And there's no point in looking for the sign, but if you want to look at the sign, the c sub 3, 1 would be negative 1 to the 3 plus 1, which is positive 1. If I want to pick m sub 2, 2, well, cross its row and column, that'll be, again, now you probably don't have to write it after a while. I'm going to write it just for the notes. And to demonstrate, it's 4 minus 0, which is 4. But c sub 1, 2 is negative 1 to the 1 plus 2. That's negative 1 to the third power. Since that's negative 1, you multiply those and you get a negative 4. Right? But there's the minor, there's the cofactor. And if I was to look at the sign cofactor list, let me see. Oh, I did m sub 1, 2. I meant to do m sub 2, 2. My mistake. Did I do m sub 2, 2? I did. That's not m sub 1, 2. So it's m sub 2, 2. And if I do m sub 2, 2, that's c sub 2, 2. That is 2 plus 2. That's negative 1 to the fourth power, and that's a positive 1. But we're going to pretty much stick with this whenever we're doing this. You're welcome to use that formula if you wish. Now, evaluate the determinant of the given matrix. If it is invertible, we're going to stop saying these things. Find the inverse. So if this is invertible, let's find the inverse. Well, let's look at how this works. First, I need the determinant. The determinant, call this A. The determinant of A would be 8 minus 8. That's 0. So this is not invertible. Remember, you have to divide by that to find the inverse. And dividing by 0 in this class is not allowed. And if I go for 8, to figure out, again, if I call this A, I'll say the determinant of A is radical 6 minus 4 radical 6. So it is negative 3 radical 6. Well, that does work. That's not a problem. Doesn't equal 0. So it is invertible. And to find the inverse, you say I'm going to take 1 over negative 3 radical 6. And I'm going to swap the diagonals. And I'm going to multiply the non-diagonals by a negative. And I end up with, let's see, negative radical 3 over radical 6. Radical 3 divided by radical 6. That will be 1/2. And negative 1/3. And negative 4, negative over negative, positive 4 over 3 radical 6. And if I take square root of 2 divided by square root of 6, that's the square root of 1 over 3. So that's negative 1 over 3 radical 3. And if you don't simplify that, that's not a problem. That's okay. I don't mind. I just want to make sure that you can find the inverse. So we say this is the inverse of A, assuming that's A. And that's how we play these things. Now, there is a formula. Again, let's not worry about the figures. I'm just putting that in because the book talks about it. 2 by 2, you run this way minus this way. 3 by 3, you start at the left corner, just like you did right there, and you run across, multiply, 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 minus those 3. So for a 3 by 3, we have a formula. For a 4 by 4, there is no formula. Use the arrows or use the shortcut to figure this out. So this is what you do. You take a matrix and you copy the first 2 columns. There is another formula as well. You copy the 2 rows on the bottom, but let's stick with this one formula. So you copy the first 2 rows, negative 2. You should space them properly so when you write the arrows, they match. Here we go. And if you want to find the determinant of that, you say that is, and you multiply those 3. That's negative 8 plus 742 plus what is that, 40? 40 times 6. 40 times 6, that's 240. And you subtract off these products. 3 times 1 times 6, that's 18. Plus 4 times 8 is 32. Plus 20 times 7, that's 4140. And this turns out to be 240. Let me just check. 240. 240. That's 198. That's 190 minus 140, 172, 180, 190. Oh, the determinant turns out to be 0. This is not invertible and I can't find the inverse. If I do the same here, again, this is a good practice. For a 3 by 3, I would list the first 2 columns, negative 1 and 1, 3 and 0, 1 and 7. So the determinant will be the product of those, that's a 0. The product of those, that's minus 5. And the product of those is 42. Minus the product of those, that's also a 0. That's a positive 35. And that's plus 6. So we're looking at 42 minus 5, which is 37 minus 41. And here I'm looking at a negative 4 for the determinant. And that's basically it. Now this is something that we do much later, something called eigenvalues, eigenvectors. We want to make sure we practice this. If I want to find the determinant of A, they say find lambda for which the determinant of A equals 0. Forget the find lambda. Take the determinant of A and set it equal to 0. If I want to pick a row or column, now I could use the shortcut. But do you see here that I have either those zeros or those zeros. It doesn't matter which two you pick. If I decided to pick this row, then I'm going to say it's going to be positive lambda minus 4, right? Cross everything in its row and column. And here, wouldn't that be the product of those minus the product of those? Now, 0 times anything is 0, and 0 times anything is 0. That's all there is. This is the determinant. Set it equal to 0. And something you're going to do later on, lambda minus 4, isn't that lambda minus 3 and a lambda plus 2? So lambda would be a 4, 3, and a negative 2. And much later, we're going to find this, and those are going to be called eigenvalues, something crucial for our applications. If I wanted to do number 18, I could pick any row or column, it doesn't matter. Now, it would be very wise for me to either pick that row or that column. It doesn't matter. If I decided to pick that column, well, 0 times anything is 0. So I could say 0 times 4, 0, lambda 0. That doesn't matter. Plus or minus 0 times anything is 0. The only piece that would be left would be positive lambda minus 5. And if I cross that row and column, I'm left with, again, you don't need to write it. You could do that automatically. You could say, well, that is lambda minus 5 and lambda squared minus 4. Lambda minus a negative 4 is plus 4. And you want to set that determinant equal to 0. That's lambda minus 5 times lambda minus 2 squared equals 0. So we get lambda equal 5 and lambda equal 2 multiplicity 2. Not to worry about multiplicity. When the time comes, we'll talk about what that means and what to do in the event that you come across one of those. Okay, well here. Now number 20 has A through D. So they say do column 1, column 2, column. I'm going to pick as well on the homework. I'm going to have you just do one part. So I picked D. There's A, B, C, D. Find the determinant by using cofactors. These are the cofactors. And I want to pick the second column, meaning I want that. Well, it's fairly simple. You take negative times a positive. So determinant is going to equal determinant of negative 1, 1, 2, 3, 0. Actually, it's easier. Just call this A. And determinant of A would be, and let's see, positive times a negative, that's a negative 1. Cross its row and column. That is 6 minus, so I could do that straight. I really don't need to write that. That will be 6 minus a negative 5 plus 5, right? Let's go back. Positive times 0. 0 times anything is 0. And negative times a positive is a negative 7, but I could say that's negative 7 times cross its row and column. I could say that is a 5 minus 6 automatically. You could write it out. You really don't have to. Oh, sorry. I messed up. I copied the wrong thing. So if you cross the bottom row and column, you get 1, 3, 2, negative 5. And again, you could say that's negative 5 minus 6. So I'm looking at negative 11. That's plus 7. I'm getting a negative 4. The determinant of this will be a negative 4. All right. We have a theorem here, something very important to keep in mind. This is going to come up later on. And some of the homework problems, we're going to aim to make it look like that. So, just bear with it a bit. And it says if you have a square matrix, upper triangular, lower triangular, or a diagonal. So a diagonal, or upper triangular or lower triangular, It turns out that the determinant of A is simply the product of those. You could have, let's say you have a 3 by 3 upper triangular, or you could have a lower triangular. The determinant in each case will simply be, and you could tell by picking a row or column, that's easy to see. So in this case, evaluate the determinant of the given matrix. Well, let's see how that plays. And if I want to figure out the determinant, call this A. Since this is a diagonal matrix, it'll simply be 2 times 2 times 2. And here it's a triangular, so it'll be the product of those. That will be 12 times 2, so determinant of A will simply be 1 times 2 times 3 times 4, which is 24. And here again, this is a triangular matrix, you could tell that. So determinant of A will simply be the product of those. That will be 6 negative times negative, that's positive, times 3, that will be 18. And that's basically it for this section. These are the problems I'd like you to look at.